So here we are with the fourth video of Unit 6B. This is the ideal gas law. We're going to begin by reviewing a little bit about pressure, how kinetic theory of matter relates to pressure. We're going to be able to look at the effects of pressure on a gas and how we can change pressure and other variables and be able to develop the ideal gas law. So let's just jump right into it. Here we go. So we can explain the behavior of gases and the origin of pressure using the kinetic theory of matter. Within any system of gas, there's a huge number of particles that are smashing into each other and into the walls of whatever container that gas is in. Those collisions transfer energy and exert forces on the particles of the container walls and on each other. Each time then that a gas molecule smashes into a container wall, it pushes outward. It exerts a force on the wall. Add all these forces up and you have an average force that is fairly constant over time. If you divide that average force by the area, you get pressure. Now we can use the fact that pressure in a gas is due to the collisions of particles with the walls of the container to make some qualitative predictions. Imagine that you partially inflate a balloon. Inside the balloon then there's air molecules smashing into each other and into the interior surface of the balloon. It's pushing it outward. But there are air molecules on the outside of the balloon having collisions with it too, pushing it in. An equilibrium develops in which the force pushing in on the balloon is equal to the force pushing out on the balloon. So the balloon stays the same size. Now, if you blow additional air into the balloon, more air molecules means more collisions with the inside surface of the balloon. So the balloon is pushed outward and the balloon gets bigger. Eventually, the balloon is big enough so that there's more collisions with air molecules on the outside. Eventually, the force from the outside collisions becomes equal to the force from the collisions on the inside. A new equilibrium is reached and the balloon has a new size. So what that leads us to is that increasing the number of particles leads to an increase in pressure. Now, if you have a container filled with some gas and we were able to decrease the volume of the container, so you take your balloon and you squeeze the balloon, the gas particles would have more frequent collisions with the walls of the container. These more frequent collisions mean that there would be a greater amount of force exerted on the walls of the container. So that pressure would increase again. So that tells us then that decreasing the volume leads to an increase in pressure. And finally, if we increase the temperature of the gas in our balloon, as we've seen, any increase in temperature results in particles gaining kinetic energy. When they gain kinetic energy, the collisions with the container they're more forceful, they push harder, so the force increases, so pressure increases. So if the system cools, just the opposite happens. So that tells us is increasing temperature leads to an increase in pressure. So this gives us four variables to work with. First, pressure, then number of particles, volume, and temperature. We can relate all four of these in the ideal gas law. These predictions then tell us that pressure is directly proportional to the temperature of the gas, it's inversely proportional to the volume of the container, and it's directly proportional to the number of gas particles. Careful experiments back up each of these predictions, so it's not hard to do a quantitative extension of this qualitative treatment that looks at the collisions with the walls and the resulting forces. This theoretical analysis leads to the same proportionalities as we see here, and ultimately produces a single equation that can express these proportionalities. That's this equation here, where this constant ends up being Boltzmann's constant. So we can write the ideal gas law as PV equals NKBT, where this is Boltzmann's constant, and this N is the number of particles in the gas. Now remember, as we saw in our last video, getting the number of particles, this is the full number of particles. We would take the number of moles multiplied by Avogadro's number to get the number of particles. You also have to remember that whenever we're using the ideal gas law, we have to make sure that the pressure here is the absolute pressure in pascals, and the temperature is the absolute temperature in Kelvin. Now, as you can see right here, I'm calling this the ideal gas law version 1, which implies there's going to be a version 2, right? This version 1, it's just the ideal gas law written in terms of the number of particles in the gas. If you've taken chemistry, you may have seen another version of the ideal gas law, which we call version 2. Because the number of particles is really just the number of moles times Avogadro's number, we can rewrite the ideal gas law in terms of the number of moles, which is this one right here, PV equals nRT, where this N is the number of moles of gas, and this R here is the universal gas constant. Temperature, again, is in Kelvin, and pressure, again, in absolute pressure in pascals. Now there's different values for the universal gas constant based on what units you're using. Okay, if we're using the SI system, our universal gas constant is 8.31 joules per mole Kelvin. Typically in chemistry, you're dealing with volume in liters and your pressure in atmospheres, and so you end up using this value for your universal gas constant, 0.821 liter atmospheres per mole Kelvin. It'll be important for you to make sure you're using the correct gas constant of 8.31 joules per mole Kelvin. Okay, so that'll do it for the ideal gas law. From here, we're going to look at processes of ideal gases. We'll see you then.